Um, this is continuation of the limit and continuity lesson. This time we want to give a numerical example. So let's see what happens when we have f of x equal to x squared. Let's just take x values that are getting closer and closer to um, 2, because we're planning to see as we go like this, we get closer and closer to 2 from below. As we go like this, we get closer and closer to 2 from above. And this is, so if you plug in these x values into the function, you get these y values. These are all y values that you get by plugging it into the function. And as you get plug in this x values into the function, you get these y values. Uh, as x values approach 2 from below, what is happening with the y values? You can see that the y values are actually approaching a number 2. What is your prediction? Oh, I say they're getting closer and closer to 4. Um, and as we go from above and we approach x equal to 2, y values also approach y equal to 4. And so this is a numerical example of the fact and that we can see that x, the limit of f of x as x approaches from below and above is going to be equal to 4. And so if this limit is equal to 4 and this limit is equal to 4, then the limit period is going to be 4. The limit from left is equal to limit from right, and it's equal to this one should be plus. So if limit from left is equal to limit from the right, and then they're both equal to 4, then the limit is going to be equal to 4. Also notice that not only the limit approaches 4, but if I plug in 2 into the function, I will get a 4 in here. Now here, if I had a graph, I could, and this is again the graph of y equal to x squared. If you look at the red points, they have x values that are approaching 2. If you look at the green points, they have x values that are approaching 2. Both points are the y value of both sets of points is approaching 4. And in this case, the value of function at 2 is going to be 4 as well. So that's another example. And this I'm soon going to talk about continuity. That's the part. And so let's say the interesting part of it, what makes continuity, or what leads to definition of continuity, is that prediction of both sides of the graph is going to be the same for y values, and then the y value of the point that we're approaching is going to be the same as that prediction. That gives us continuity. So this road, the purple road, is predicting that x values are going to, y values are going to approach 2 as x approaches -1. And this blue part is telling us that y values are going to approach 2 as well as x is approaching -1. But on the other hand, the point -1 and 2 is part of the graph of the function. That's the prediction of the blue. and prediction of the purple are the same as the value of the function. That is actually continuity. So limit from left equal to limit from right equal to value of the function. Now, how about here? This part of the graph is predicting that y values are approaching 1 as x values are approaching 2. This part of the graph is telling you, the red part of the graph is telling you that values for y are approaching 1 as x is approaching 2. But the point 2 and 3 is on the graph, the orange point up there is telling you that the prediction of the two sides of the graph, the prediction of the neighbors of the point is not the same as the point. And that's sort of a discontinuity of the graph. You see a hole in the graph. Now, for x equal to 3, what do you see? So you see the prediction from the right side of the graph is telling me that as we approach x equal to 3, y value is going to be 1. The prediction of the right side of the graph is no prediction at all. And that is the limit doesn't exist from the left side of the graph. Therefore, again, there's a discontinuity. And look at this. When I'm talking about discontinuity, I'm literally talking about a broken graph or a hole in the graph or something like that. And so, and you discuss the limits and you discuss um, the also the continuity in the graph. Oh, there's always this discussion that I have. If you are on this path and you're approaching 2, and then instead of going to 2, you suddenly teleport to another point up there. See? That is a point of discontinuity. I'm approaching from the right and I'm supposed to end up at this point, but instead I teleported over there. That's the point of discontinuity. But literally you can see breaks or holes in the graph, and that gives you discontinuity. The another way of doing this is if I'm tracing on the graph. Let's see, if I'm tracing the graph from one side and I'm approaching here, and then so the limit from the right exists, but I'm tracing the graph from the left and I'm not arriving at anything. So the limit from the left doesn't exist. Then the other one is tracing the graph from the right and approaching x equal to 2, and I'm arriving at something. And I also trace the graph from the other side, from the left side, and I'm arriving at a point. And so that's a limit from the left, and the two limits are equal. So all these other ways of putting it in there, see which one you're comfortable at and use it. And have it in mind that you could be tracing the entire time but not arriving at a point. Tracing the graph, you could be able to trace the graph the entire time but not arrive at any point. That's like the one example was right here, when you could trace it but not arrive at anywhere. And you could be not even being able to trace anything. That's the most difficult example, but you do arrive at a limit point. That is more difficult if you're taking analysis again, if you're taking mathematical analysis, that would be an example that can be discussed in mathematical analysis, not in any regular calculus